Yeah, so the quick way we talked about last class was that the eigenvalues of a matrix always add up to whatever the diagonal adds up to, and the sum of the diagonal is called the trace, and they multiply to whatever the determinant is. So the two eigenvalues here need to add up to 2 and multiply to 1. What does that sound like? We're looking for two numbers that add to 2 and multiply to 1. And there's only one combination of numbers that this could be. What is that combination? What does this have to be? Yeah. Yeah, 1 and 1. So this is the first matrix we've seen that has a repeated eigenvalue. Okay, that's going to be a big part of the types of matrices we look at today. What happens when a matrix has repeated eigenvalues? You had a question? So the fact that it seems like this matrix has the eigenvalue of 1 repeated twice means that it's the algebraic multiplicity of the eigenvalue 1 is 2. I'm not going to write the definition of that on the board right now. We're going to define that in a little bit more formality in just a bit. But just know that there is a term for this. The fact that it seems like 1 is repeated twice. Okay? Now, if you didn't want to use these trace tricks, the more systematic way is to take the characteristic polynomial, which is the determinant of a minus lambda I, and set that to 0. Which here, the determinant of a minus lambda I is 1 minus lambda squared. And here you can see lambda equals 1 is a double root. It appears twice here. Do we agree with that? Okay. So now the question is, what are the eigenvectors? I don't know. Let's find them. What are the how do I find the eigenvectors corresponding to lambda equals 1? Well, someone tell me. I forgot. How do I find the eigenvector for eigenvalue 1? Yeah.
Well, one way you could like set up a system of equations.
Sure.
You multiply like the matrix by like some random vector, which I use like AB, and then because the eigenvalue is 1, you should also get AB back.
Good. So this needs to satisfy A times this eigenvector equals 1 times this eigenvector. That gives me a system of equations here, the first of which is A plus B equals A, and the second of which is B equals B. Okay? What is the solution to this? There's not going to be just one solution, there will be infinitely many, but what are those solutions? Yeah.
0.
B has to be 0. Right? The second equation doesn't tell you anything. It just says B is equal to whatever B is. Yeah, like we knew that already. In the first one, if we subtract A from both sides, this says B is 0, and A can be anything. Okay? So that means the eigenvector, the set of eigenvectors is all matrices or all vectors that are scalar multiples of 1, 0. So 1, 0 is an eigenvector. Okay? And just to double check, if you multiply A by 1, 0, what do you get? Well, in the first row, you get 1 times 1 plus 1 times 0, which is 1. And in the second row, you get 0. So it does track that this is an eigenvector. Okay? Now, what I just wrote down on the slide 2 slides ago, 1 slide ago, was that when we were doing this analysis about the long run behavior of a Markov chain, we needed the eigenvectors of A to span all of Rn. But here, the only eigenvector of A is just the vector 1, 0, and its scalar multiples. So despite this being a 2 by 2 matrix, it doesn't have two separate eigenvector directions like earlier examples did. It's a 2 by 2 matrix, but it only has one eigenvector direction. Its set of eigenvectors for lambda equals 1 is just the x-axis, anything comma 0. Do we see the conundrum here? Like, it's a 2 by 2 matrix, but it only has one eigenvector direction, right? And so the eigenvectors of this A don't span all of R2. So if I draw out R2 here, what I'm emphasizing here is that A, which is 1, 1, 0, 1, only has one line of eigenvectors for lambda equals 1. And the other thing I'm emphasizing is that A's eigenvectors don't span all of R2. Okay? And there's a term for matrices like A. And the way I want you to think of A is that it's like not living up to its full potential. Here's what I mean. It's a 2 by 2 matrix, which means at most it could have two linearly independent eigenvectors. It doesn't though. It only has one. Okay? So it doesn't have as many linearly independent eigenvectors as it could. Okay? So, for reasons I'm about to describe in just a bit, A is not diagonalizable. So what is a diagonalizable matrix? It's one that does have n linearly independent eigenvectors. Okay? Now you may initially think that the source of concern here is the fact that A had a repeated eigenvalue. Like, does that mean it is not diagonalizable automatically? Well, here's another example. What if A was just 1, 0, 0, 1? What are its eigenvalues? What are its eigenvalues? Yeah.
1, 0.
Not quite. For it to have an eigenvalue of 0, it would have to mean it's not invertible. And we'll talk about that a little bit more in a bit. But yeah. Yeah, it's just the same as before. Also has lambda equals 1 as a repeated eigenvalue. Remember, the surefire way to determine what the eigenvalues are if you can't tell by looking at it is to just find the characteristic polynomial, which is the determinant here of 1 minus lambda, 0, 0, and 1 minus lambda, which is 1 minus lambda squared. Right? There are some tricks you will develop for quickly spotting eigenvalues, and these are discussed in the notes. One of them is that a diagonal matrix, its eigenvalues are the things on the diagonal. Another trick is that for a triangular matrix, either upper triangular or lower triangular, the eigenvalues are also the things on the diagonal. So here, because this is upper triangular, I could have just looked at the diagonal. Okay, and we will see more examples of this in a bit. Anyways, the idea here is that this matrix has a repeated eigenvalue. It has an eigenvalue of 1 that is repeated twice. But this matrix is different than the previous example. And what makes it different is that it does actually have two linearly independent eigenvectors. How would I find them? Well, I can try and set up the same system as before. I want 1, 0, 0, 1 times AB to be equal to AB. And when I work this out, the first equation gives me A equals A, and the second gives me B equals B. And here, both variables are free. Which means it doesn't matter what A and B are, the resulting vector, A comma B, is an eigenvector of A. Everything is an eigenvector of the identity matrix, 1, 0, 0, 1. Okay? So does this matrix have two linearly independent eigenvectors? Sure it does. Because to span the set of all of its eigenvectors, I can do that using 1, 0, 0, 1. Or I could do it using any two linearly independent vectors in R2. Okay? And so maybe another way to make this make a little more sense is the set of all eigenvectors of A for this one eigenvalue of lambda equals 1 is a two-dimensional subspace. Of R2. With the caveat that we defined an eigenvector as being not the zero vector, because anything times 0 is the zero vector. So we'll say it's a subspace, but ignore the zero vector. Okay, what was the point here? My point was that just because a matrix has a repeated eigenvalue doesn't automatically mean it doesn't have n linearly independent eigenvalues, or eigenvectors. Because this matrix does have repeated eigenvalues, but it does have two linearly independent eigenvectors. Okay, and its eigenvectors do span all of R2. In fact, all of R2 is the set of eigenvectors for lambda equals 1. So there's something worse about 1, 1, 0, 1, in that it has a repeated eigenvalue of 1, but its eigenvectors don't span all of R2. Do we see the subtle difference between 1, 1, 0, 1 and 1, 0, 0, 1? So between this slide and the other slide, the matrices are a little different. We buy that, right? Okay. So keep that thought at the back of your mind. I want to use this idea to discuss what is sometimes called the eigenvalue decomposition of a matrix. Let's suppose we're dealing with a matrix that does have n linearly independent eigenvectors. So let's say AV1 equals lambda 1 V1, and AV2 equals lambda 2 V2, and AVN equals lambda n Vn. Note that some of the lambdas could be the same. Like if this were the identity matrix, all of the lambdas would be equal to 1, for example. Okay? That's not an issue. What I want to try and do, here's what we're working towards, is come up with a decomposition of A. What are some decompositions we've seen before? One of them that we saw towards the beginning of our study of matrices was called the CR decomposition, right? Where we said A equals C times R. Here I'm looking for A equals something times something times something. And those somethings should involve the eigenvalues and eigenvectors of the matrix. And this seems like a random thing to want to do, but I'll show you the utility of it in just a second. Here's how I'm going to come up with this eigenvalue decomposition. Check it out. First, do we agree with these n equations over here on the left? AV1 equals lambda 1 V1. AV2 equals lambda 2 V2. This is what it means for V1 through Vn to be eigenvectors of A. All right? What would happen if I tossed all n of these eigenvectors, V1 through Vn, in a matrix, and I turn them into columns of a matrix? So here's what I mean. Suppose I make a matrix whose first column is V1, whose second column is V2, and whose last column is Vn. So this matrix, I'll call it V. What happens when I multiply A by V? Firstly, what is the shape of the output going to be? A is an n by n matrix. What is V? What is its shape? Capital V. Yeah.
Just n by 1.
Capital V, the matrix V. How does that change your answer? There are n vectors. So the number of columns in this is n. How many how many numbers are in each V?
So
N. It's also an n by n matrix. So the result also needs to be n by n. You multiply two n by n's, you get back an n by n. What is the first column of that result going to look like? Remember, way back when we first studied how matrix multiplication works, one of the ways to think about it is that the first column of the output comes from doing A times the first column of V. And the second column will be A times V2. And the third column will be A times V3, and so on. Do we agree with that? Right, that's the way you multiply matrices by hand. You multiply A by the first column, and that gives you the first column of the output. Do we agree with that? So, in this outputted matrix, the columns are going to look like, you know what, we're going to need more space for this, so let's just make a new slide. The columns are going to look like A times V1, A times V2, all the way through A times Vn. But we can simplify AV1, AV2, all the way through AVn. What do those simplify to? Because the V's are eigenvectors of A, what do they simplify to? They're still vectors, but what are they? Like I can write this not involving a matrix. Yeah.
Which is like lambda, whatever it is, times the vector.
Exactly. Lambda 1 V1 is the first column, and lambda 2 V2 is the second column. And lambda n Vn is the last column. Okay, here's where the big step comes in. Turns out I can rewrite this as the product of two other matrices. Take a moment and think about what those two other matrices would be. So I can factor this matrix. I'm not saying write it as A times V again, because I started with A times V. I want to show that A times V is equal to something else times something else. And then I can rearrange that equation for A. Remember, my goal was to solve for A. It's A equals something times something times something. So think about how I might be able to break down this new matrix, whose columns are lambda 1 V1, lambda 2 V2, all the way through lambda n Vn, how I might be able to break that into two other matrices. Give you a moment to think about that. I'll do a lap and we can take it up.
Yeah, it's like hard, but I'm like, you probably need to click all these activities. Yeah, until I click all the activities. I was thinking that I just didn't know like how to arrange it. Like that was my.
Yeah, because like
I like set it up like first week.
preserve the lambda v together so it can be lambda.
All right. Did you think of a way to factor this new matrix into two other matrices?
Wouldn't be like the diagonalization of like.
Yeah, well, what I'm getting at is one of these matrices could be a diagonal matrix with the lambdas on the diagonal. Now the question is, which matrix is that? Which one is it? The second one. Yeah, this is a little tricky for me to wrap my head around too, but let me write this in and then we can talk about it. What I was getting at is the first matrix has as its columns the eigenvectors v. So this first matrix is really just the same v that we defined at the start of this expedition. The second matrix has on its diagonal the eigenvalues and zeros everywhere else. Now again, how do we do matrix multiplication? What we do is we multiply the left matrix by each column of the right matrix independently. So what is the first column of this product going to be? Well, it's this whole matrix times the first column of this diagonal matrix, which is lambda 1, 0, 0, 0, 0, 0. And all of these zeros correspond to canceling out v2 through vn. And so the first column of the result, v times this diagonal matrix, is just lambda 1 v1. But that matches what we found up here. So it means we did our decomposition correctly. So big picture, what did this buy me? Well, I'm going to define. What did this buy me? What I'm going to do is I'm going to take this diagonal matrix of lambdas and give it a new name. Also lambda, but we're going to make it the capital Greek letter lambda. And so if I look at what's on the page here, I have A times V equals V times lambda. Now remember, I told you my goal was to say A equals something. How do I solve for A here? Sorry, how do I solve for A here? Yeah.
You can try inverting v if it's invertible.
Yeah. The key is, in order to solve for A here, V has got to be invertible. But what would make V invertible? How does this have anything to do with the other stuff I was talking about? Yeah.
Like vectors would have to be linearly independent.
Exactly. All of the V's, V1 through Vn, would need to be linearly independent. But V1 through Vn were eigenvectors of A. So that's why the linear independence of eigenvectors is important. If A has n linearly independent eigenvectors, well then this matrix V that is made up in its columns of the eigenvectors of A is invertible. Okay? So if A has n linearly independent eigenvectors, then V, who I not invented, but created by placing A's eigenvectors into its columns, is invertible. So if V is invertible, how do I solve for A here? Well, I got to multiply both sides of AV equals V lambda by V inverse. And what that buys me is A equals V capital lambda V inverse. And this is what's called the eigenvalue decomposition. Now, who cares? Like, what am I going to do with the eigenvalue decomposition of A? Well, here's one quick application of it. Suppose I have the eigenvalue decomposition of a matrix A into V lambda V inverse. there was an operation with matrices that we did a lot of in Monday's lecture. One that could get inefficient if we had to repeat it many times. What was that operation? We used it a lot in our simulations. Yeah, the powers of a matrix. And you're going to do a little bit of this in tomorrow's lab as well. Matrix powers become really easy to calculate once you have the eigenvalue decomposition of a matrix. Why is that? Well, let's see what happens if we square A. What's going to happen? I'm going to have V lambda V inverse times V lambda V inverse. But check it out. I have V inverse times V, and we know that that's just the identity matrix. And so this becomes V lambda lambda V inverse. That just looks like to me V lambda squared V inverse. Now, this seems not any simple. If you just look at the symbols, this doesn't seem any easier than just squaring A. But why is this easier? Like, why is calculating V lambda squared V inverse and multiplying those easier than just multiplying A times A? What is better about this? Yeah?
If lambda is a diagonal matrix, well, 0 squaring it is just squaring every other.
Exactly. Remember, lambda is a diagonal matrix. The only things in lambda are the eigenvalues of A, and those live on the diagonal. So squaring a diagonal matrix is really easy. You just square the things on the diagonal. You don't have to do the whole complicated matrix multiplication procedure. Capital lambda squared just looks like this. And that's really simple to compute. So for example, if for some reason I needed to find A to the 100, well, that's filling in the pattern, V lambda to the 100, V inverse. So all you really need to do this are eigenvectors and eigenvalues of A, and then you can, with just one matrix multiplication, or two, V times lambda, and then lambda times V inverse, calculate that power. So I'll say way more efficient than multiplying A by itself 100 times. The other application of this eigenvalue decomposition is that it helps us more easily understand how linear transformations work. But I'm going to save that analysis till the end of the lecture when we talk about a special type of matrix and its eigenvalue decomposition.